Back everyone, it's Berat again, and in this video we will talk about Quantum Fourier Transform and how we can implement it using Qiskit. Okay, as you may remember, the definition for Quantum Fourier Transform was this, where Wn is just the nth root of unity, and this big N is simply 2 to the power little n, which I will call n from now on, and this n is just the number of qubits that we have. Okay. Let me quickly go over the derivation in Qiskit textbook for the circuit of Quantum Fourier Transform. Okay. In the first and the second steps, there is nothing new. We just write the definitions in it. And if you notice, this y over 2 to the n is simply can be written, if you think y as a number that is written in binary, and if you divide it by 2 to the n, the number of digits it says, you can just write it down as this. Okay, it will just be 0.y1, y2, and all the way up to yn. Now, while going from here to here, what you do is basically realize that this summation can be written down as a product, right? Because you have exponential and you have exponential sum. And for each term, you just have yk over 2 to the k. Okay. Now, while writing all of these as a tensor product in here or in here, what you need to realize is while y, the whole number, like yn, y1 all the way up to yn representing y, this goes from 0 all the way up to big N minus 1, right? And along this summation, what you can do is you can write each digit as going from 0 to 1. And you can write this down for each digit. So what you have is, you can kind of separate the, for example, the first one from the rest of it and the second one from the rest of it by writing it in such a form. Okay, when you separate y1, for example, as a tensor product from the rest of it, what you have is you have two cases where y1 is 0 or 1. When it's 0, the state in here will be 0 and the coefficient in front will just be 1 because it will be e to the power 0, right? Plus, when y1 is 1, you will have a 1 state, and in it you have a coefficient, and for this specific case you will have e to the 2 pi I x over 2, right? You just write y1 is equal to, k is equal to 1, and you just get this state. So if you write this down for all of the states, you will see that QFT maps a state to another tensor product state, so we can actually implement the circuit easily. If you note that you can achieve this superposition by applying a Hadamard, and you can write down this, you can achieve this phase factor by applying a controlled rotation. Okay, now let me just say something before I move on. In your lecture notes, it's not written down as, like in here it will be j, it's not written as 2 to the pi I j over 2 to the k. Okay, but actually they are equivalent. If you think about any integer number, for example, in this case, when you divide x by 2, what you have? In this case, you will have x1, x2, and all the way up to xn minus 1 dot xn, right? You will have an integer and a fraction. And you can just write this down as two products, integer part and the fraction part. An integer part, for example, will be e to the pi I times x for some integer x. Well, you can just take this out, and this will be e to the 2 pi I to the power x. Well, this guy is simply 1, so this will just be 1. So these two notations, the one that is in Qiskit and the one in here, is equivalent. But this one will give us a more intuitive idea of what Quantum Fourier Transform does. Okay, now that we've got this ultimate tensor product form in our hands, we will be able to write down the circuit for it using this RK gate. More specifically, controlled RK gates. I realized that this was not a complete derivation, so there might be parts that you just missed or couldn't understand. I strongly suggest for you that you just go ahead, do the arithmetic for yourself, then you will understand that it's quite trivial and really easy to see. But you should do it for yourself. So we have the circuit, like we kind of have the formula to implement the Quantum Fourier Transform, but we just don't know how will we implement this RK gates, okay, control rotation gates. Well, turns out in Qiskit we have like this CU1 gates, which takes 3 arguments: rotation angle, control, and target qubits. Okay, and this is just what we need if we provide the arguments 2 pi over 2 as 2 pi over 2 to the k. Okay, so for example, for R2 the argument of rotation will just be pi over 2. Okay, for R3 it will be pi over 4, and etc. If we just write down a quantum Fourier transform circuit on 4 qubits, you will see exactly what we mean and you will get used to it. Okay, let's say our input is x, which is just a 4-bit string, and this is the circuit that implements quantum Fourier transform on it. I mean, you can just go ahead and check and that it doesn't do anything extraordinary. These guys are just representing swap gates, okay, because when you apply this operation you will obtain y3, y2, y1, y0, so you need to swap these. Now if you have a general look, you will see that the operation that we are performing, QFT, consists of 2 parts. Okay, the first one is rotating and the second one is swapping. Okay, now we will just write down this circuit one by hand, like each gate in Qiskit, and run it. Okay, what do we need? We need the value of pi. We don't actually need this guy. We need a quantum circuit object. We will execute it, and we need a backend. Okay, you will also see what this block multivector is. Okay, so let's initialize our quantum circuit. I mean, for simplicity, let's start with 000 state. Okay, we don't perform anything on the qubits. So we just start applying our QFT. We apply a Hadamard gate to the most significant qubit, then apply rotation gates. I mean, the first rotation will be CU1 pi over 2, and the second one will be pi over 4. This one will be pi over 8, and the control qubits will decrease, but the target qubit will stay the same. Okay, that's exactly what this does. We put a barrier, so we get a nice looking circuit at the end. Afterwards, we go on to play with the second qubit, apply a Hadamard, a CU1 pi over 2 rotation, and a pi over 4 rotation. Okay, that's what we do here. And we go on to the X1. We just apply a Hadamard, a pi over 2 rotation, again a barrier, and finally we apply Hadamard to the least significant qubit. Now we have the quantum Fourier transform of this state, but it's reversed. So we apply some swap gates and get our result. So let's quickly draw our circuit. Let me uncomment these. You can see that this is exactly the one, like the one that I've drawn. Okay, let's run this circuit with state vector simulator. Okay, and see what the resulting final state is. Well, this doesn't really tell you much, but if we use plotability, this function, you will see what it does. Okay, we started with 000 state, and all of the qubits are mapped to plus states. Okay, well, this is actually what we should expect, because if you look at the circuit in here, if all the qubits in here are in 0 state, none of the rotations are applied, right? Because they are controlled operations. So we only applied Hadamard gates. So each Hadamard gate maps 0 state to plus state. So we applied the Hadamard gate to each. Swapping again didn't change anything. We got this final state as plus. Let's do something a little more interesting. Okay, so we can go ahead and initialize our initial state to 0110, for example, where in this case x, like the value of x, will be 6, right? We can go ahead and initialize our circuit. Okay, nothing to see in here. Now the state vector in the final state, it looks a little more complicated than the previous one. Okay, and if we just plot the Bloch vectors, like the Bloch sphere representation of each qubit after we performed it, you will see that it's not so trivial. Okay, let's see how did we get this result. Okay, now if we look at this formula that we have in here, Okay, one thing to note that this is in reverse. Okay, so this guy represents the below sphere of this guy. So this below sphere represents this guy, and etc. So our x value, for example, in our case, this n is simply 4. So this 2 to the n is 16. And this x value is simply 6. So this will be rotated by 6 over 16 full rotation. So in other words, 3 over 6, or it will just be rotated 1 over 4 plus 1 over 8 times, right? So probably it's just rotated 1 over 4 times plus 1 over 8. So in total 3 over 8 of full terms. Now what about this guy? This guy will be what? X over 2 to the n minus 1, or simply x over 6 over 8, or 3 over 4. You can see that this is rotated 3 over 4 full terms. This guy will be rotated 6 over 4, so this is like 1.5. So this returned, this is rotated once and a half. And this guy will just be rotated 6 over 2, so this is like rotated 3 times. Okay, that's what this multi-vector representation, multi-block vector representation represents. You can just go ahead and play with it if you like. You can just like change this initial values, check that how much they are rotated around z-axis, and just confirm your intuition. So that's what it does. Okay, so let's move on to something more general. I mean, how will we write down a quantum Fourier transform function that will just take a circuit and the number of bits it has, the number of qubits it has, and just applies a QFT on it. Okay, so if you just analyze the structure of quantum Fourier transform circuit, as we have said before, you have like 2 stages. The first one is the rotation part. You just apply a lot of rotations at first, then you just swap the registers, like do a bunch of swap operations. Well, we can just use this in our general circuit, right? General function. Write down 2 functions, like QFT rotations and swap registers. And use this in our general QFT function, okay? This QFT rotations and swap registers function. This swap registers is quite trivial, okay? So there's no need to focus on it, on what it does. This QFT rotations functions, however, is quite cleverly written. I mean, I just copy pasted it from Qiskit textbook. So what it does is actually quite clever. If you have a look at the quantum circuit that we have, it kind of has this recursion structure. Okay, you start with, for example, 4 qubits. You want to apply a 4 qubit quantum Fourier transform, and what do you need to do? You just need to apply this rotations to the most significant guy, in this case the 3rd index qubit. The first thing you do is apply a Hadamard gate. Then all the way up to the 1st qubit, you apply controlled rotations by increasing the angle. Okay, and the angle for each rotation is just the distance between each index. So if this is like the index qubit, and this is like, let's say this is the index I and this is index j, you will rotate it by pi over 2 to the I minus j times, right? So we can actually write this down for 4 qubits, let's say, and to apply this to a smaller circuit, we can just call QFT rotations with a smaller index, right? So we can just apply recursion. So that's what basically this function does. It basically first defines a basis case when n is equal to 0, right? You need to define this while defining recursive functions. If that's the case, it just returns. Otherwise, it just decrements n by 1. Okay, it applies Hadamard to the most significant qubits. Exactly what I stated. Then all the way up to the 1st qubit, okay, 4 qubit in range, and it just keeps on and applies controlled rotations where the angle is just the distance between them, 2 to the power distance between them, like pi over 2 to the pi over distance between them, and you just move the control qubits one by one to the up. Then at the end, once you're finished with the most significant one, you just go ahead and call the function again. But this time this n will be reduced, So if this was 4, this will be 3, and it will be called again for 2, and it will be called again with 1, and it will be called again with 0, and it will just return. Okay, this will basically just finish this applying this rotations part. And what we need to apply swap registers. So if we just include these two functions and combine into one function, we have a function that applies, a general function that applies quantum Fourier transform. I mean, this is quite easy compared to the Simon oracle that we've covered last week. But this week, as something different, I have an exercise for you. Now, in oracles.py function, I've defined a QFT oracle function, okay? This basically generates a random bit string, okay? And initializes the quantum circuit that you have to that bit string and applies quantum Fourier transform to it. But it also returns this secret bit string for you to do your comparison, okay? Now what you need to do is write the inverse quantum Fourier transform function. Okay, you know how to write down quantum Fourier transform. So you can just take its adjoint, find out what this inverse quantum Fourier transform looks like. Okay, and you just write down the function for it, just like the one in here. Okay, once you've written this down, I just want you to apply this, uncomment this line, and just execute it with the state vector. I mean, for example, for a state n equals to 4, sorry, I mean, this is the oracle that I've written down. Well, probably it produced some bit string, but it didn't apply some quantum Fourier transform. So if you just go ahead and run, you will just see what? You will see the quantum Fourier transform version of it. Well, you should be able to tell what the secret bit string was from this below spheres. It was 0, 0, 0, 0. Well, if you just go ahead, run this again, you get a different state and you get a different bit string. Okay, you can just increase n and just go ahead and play with it. But I strongly suggest you write down this inverse quantum Fourier transform function by yourselves. Thank you for listening.